Welcome to EduTatva Career Info Series. I am absolutely thrilled to be your explainer today as we unpack one of the most demanding, fascinating, and high-stakes fields out there. We're taking a deep dive into aeronautical engineering.
You know, when most people hear aeronautical engineering, their minds instantly jump to a glamorous movie scene, right? Like sketching sleek fighter jets on a drafting table or wearing aviators on a runway while watching a supersonic jet blast off. But today, we're going to strip away that Hollywood myth. We really need to look closely at the rigorous, mathematically intense, and highly structured reality of this incredible profession. Because honestly, the day-to-day work is way more complex than the movies make it seem.
Okay, so let's dive right into this by defining our terms. Aeronautical engineering is a highly specialized branch of engineering dedicated to flight vehicles operating strictly within Earth's atmospheric layers. The absolutely crucial distinction here is the atmosphere itself. Unlike astronautics, which deals with the vast vacuum of space, aeronautics deals intensely with the unpredictable, super complex behaviors of dense air. You are constantly battling drag, crazy weather patterns, thermal dynamics, and severe turbulence. We're talking about designing and maintaining everything from commercial airlines and helicopters to unmanned drones and military jets that literally have to survive these extreme atmospheric conditions.
Here's our diagnostic roadmap for today's explainer. We'll look at the academic prerequisites to get in, map out the core curriculum, explore the professional reality of the job, and then we'll analyze the psychological blueprint, and finally, the friction and risk factors. Consider this a structured counseling session to help you figure out if you truly fit the bill for this career. Let's get started.
First up, academic prerequisites. Let's evaluate your educational background and see if you meet the initial threshold to even step onto the tarmac.
So, to pursue a bachelor's degree in this field, you're going to need to hit some very specific academic and quantitative benchmarks. First, you must complete your 10+2 higher secondary education with a super rigorous focus on physics, chemistry, and mathematics, the classic PCM. Then, you'll need to clear highly competitive entrance exams. We're talking the JEE Main, JEE Advanced, or state-level tests like the KCET in India, just to secure your spot in a BE or a BTech program. But look, beyond the grades, the real core competencies you actually need are strong spatial reasoning, like the ability to visualize how complex structural components interact in 3D space. You also need a natural intuition for fluid mechanics and analytical calculus. Honestly, if you can't visualize the math in your head, the blueprint simply won't make sense to you.
Let's move to our next section, the core curriculum, and see how this all builds once you actually get into university.
The evolution of your degree shows that the jump in complexity from year to year is absolutely massive. In year one, you're basically building the foundation with intense engineering math and fluid mechanics basics. By year two, the stakes get way higher. You're studying material science, so understanding metal fatigue, stress loads, and corrosion under flight conditions, and you're using CAD to map out precise aircraft parts. Then, year three is where the core specializations hit hard. You dive deep into atmospheric aerodynamics, wing theory, and the crazy intense physics of shockwave behavior. Finally, in year four, you apply all of this to incredibly complex systems, like air-breathing propulsion, think gas turbine cycles, and advanced avionics. It's a huge, high-stakes intellectual journey from pure math on a piece of paper to understanding exactly how a turbofan engine safely operates at 30,000 feet.
Now let's shift our narrative from the academic classroom to the physical hangar floor and corporate design labs. This is the professional reality.
And this division brilliantly illustrates the intra-field split within aeronautical engineering. The daily workflow generally splits into two massive camps. On one side, you've got aerodynamics design and R&D. This is a digital, highly abstract, virtual world where you simulate airflows, run computational fluid dynamics, and focus heavily on complex equations. On the flip side, you have aircraft maintenance, repair, and overhaul, or MRO. This is the physical, tangible, real-time world. Over here, you aren't running virtual simulations. You are troubleshooting active aircraft on the actual hangar floor. You're turning heavy bolts, and you are literally putting your signature on a legally binding document certifying that a massive passenger plane is safe to carry hundreds of people today. The pressure and responsibility there, just immense.
So where do these professionals actually work in the real world? Well, the industrial sectors are huge. You've got commercial aviation and airlines like Indigo and Air India. You have global aviation OEMs, that's original equipment manufacturers like Airbus, Boeing, and Hale. There are dedicated MRO centers ensuring absolute fleet airworthiness, and of course, highly secured defense and research labs like DRDO, NAL, and the Indian Air Force. But definitely pay attention to the rapidly booming sector in UAV and drone startups. This space is just exploding right now. focusing on everything from precision agricultural mapping to autonomous flight control and urban air mobility. It's literally a frontier that is fundamentally changing the entire aerospace industry.
This brings us to a fascinating part of our diagnostic roadmap, this psychological blueprint. Let's see if your mind is actually wired for these highly rigid environments.
Now, what's really interesting about this psychological profile is the Holland code for this field. The optimal trait shifts strongly to RIC. The realistic trait is highly dominant because, well, you're dealing with massive, tangible physical machines. The investigative trait is essential for diagnosing fluid leakages or running complex math simulations. But I really want you to look at the conventional trait. It is heavily pronounced here, and that's because of the strict safety frameworks enforced by global aviation bodies. Every single bolt turned, every single wire checked requires precise adherence to a massive manual and a formal audited logbook entry. There is absolutely zero room for guesswork. You either follow the manual perfectly or the plane doesn't fly. It's that simple.
When we look at MBTI personality types, the ISTJ, also known as the logistician or inspector, is the absolute gold standard for this field. Why? Well, because their natural respect for rules, high attention to detail, and deeply methodical nature make them absolutely perfect for ensuring flight safety. In an engineering field with truly no margin for error, an ISTJ's innate ability to meticulously manage maintenance pipelines, cross-reference safety codes, and run flawless quality checks is quite literally what saves lives.
We also see tremendous success with the ESTJ, the director, who is brilliant at operational fleet management, basically making sure massive commercial fleets stay airworthy on very tight, unforgiving timelines. And then there's the ISTP, the virtuoso. These are your hands-on mechanical troubleshooters. They possess this brilliant tactical curiosity and excel at field diagnostics. They're the ones physically taking a massive engine turbine or some complex landing gear apart right on the hangar floor to figure out exactly why it's malfunctioning and exactly how to fix it with total precision.
Now, Section 5, Friction and Risk Factors. We need to slow our pacing down for a moment and shift our tone, because we have to talk about the real risks here. Commercial and military aviation carry immense human lives at risk.
So the crucial point to understand is that not every personality is suited for this immense responsibility. And you know what? That is perfectly okay. The field simply enforces absolute standardization and deep hierarchies to maintain safety. For example, if you're a creative idealist, like an ENFP or INFP, who thrives on creative freedom and personal input, you'll likely feel pretty choked by unyielding aviation checklists that forbid any deviation. If you have an artistic dominant profile that values fluidity and ambiguity, you really need to understand that improvising a repair procedure in aviation isn't just frowned upon, it is illegal and highly dangerous. And if you're social dominant, primarily seeking to heal or provide interpersonal emotional care, the highly sterile, data-driven, machine-oriented environment of a hangar floor or simulation lab will probably feel incredibly unrewarding and isolating to you.
Which brings us to our final, provocative thought. Just look at the immense weight of this entire field. Look at the rigorous years of intense math, the unyielding global safety manuals, and the tangible reality of these massive, powerful machines. Ask yourself, do you have the precision, the discipline, and the psychological alignment to keep the skies safe? It's a profound responsibility. You aren't just building machines, you are guaranteeing human safety at 30,000 feet. But for the right person, it is undoubtedly one of the most thrilling and rewarding careers on the planet.
Thank you so much for joining me on this deep dive into aeronautical engineering. We really hope this explainer gave you a clear, realistic view of the journey ahead. Follow us for more. For psychometric-based career counseling, contact us. Keep exploring, keep learning, and I'll see you in the next explainer.